Linear functions grow at a constant rate. That is to say, they have additive growth. So let's look at this linear function, L of x equals 2x plus 3. If we plug in 1 into here, we have 2 times 1 plus 3. That gives us 5. Plug in 2. 2 times 2 is 4 plus 3 is 7. Plug in 3, we get 9 out. So we have 5, 7, 9, and then you can see the pattern. We're adding 2 each time. So the next one would be 11, then 13, then 15, then 17. All we have to do to find the next number is add 2, which is the slope. And that's the key thing with linear functions, is they have constant rate of growth. All you have to do is add the slope to the previous number to get the next one. Now, exponential functions are similar, but instead of adding, we're going to multiply to get the next number. Simple exponential functions are in the form exp of x equals b to some power of x, where b is it's called the base, is greater than 0 and does not equal 1. If it was 1, it'd be 1 to the power of x, then any number you plug in there is just going to give you 1. So it's kind of a pointless thing. It's a constant function. It's not really exponential. So with these restrictions, that allows us to have a continuous function, one that we can graph and do all of our analysis on that we're used to doing. Now, let's look at this exponential function here, where b equals 2. So 2 to the power of x, we plug 1 into there, we get 2 to the power of 1, that's just 2. Plug 2 in, we get 2 to the power of 2, that's 4. Plug 3 in, 2 to the power of 3 is 2 times 2 times 2, so that's 8. You get 2, 4, 8. Next one would be 16, and then 32, 64, 128, 256, and so on. To find the next number, all we have to do is multiply by 2, and that is the base of the exponential function. So the basic exponential function, b to the x power of x, is this graph here. We've actually seen this a number of times before, and I should say that this is actually b greater than 1. We're going to look at b between 0 and 1 in just a moment, but this is specifically for that. That's how you get this behavior. The domain of this is everything, because if you look back at this one here, right, we can plug in any number into x. Any small number that's going to be 1, like for instance, negative 10. 2 to the power of negative 10 is just 1 over 2 to the 10. And we can find that. That's just, 2 to the 10 is just a number that we can find. It's a very large number, but it's just a number. And then 1 over that, it's going to be a very, very small number, close to 0. If you plug in any really big positive number, like 1 million, 2 to the million, well, that's going to be extremely large, but it is still findable. You can find it. Maybe a calculator can't calculate it because it would actually overflow, but it is still a valid thing to calculate. You could do it by hand. Now the range, this we've talked about before with parent functions of this thing. As the x power on 2, for instance, gets more and more negative, so 2 to the negative 100, you're going to get 1 over 2 to the 100, 2 to the negative 1000, you're going to get 1 over 2 to the 1000. You can see that these numbers are getting smaller and smaller and smaller. They're not getting more negative, they're just getting closer and closer to 0. So the range is actually from 0 to infinity. And I have to use a parenthesis because it never hits 0. It gets close to it, but it never hits it exactly. So it never crosses the x-axis. With that in mind, then, the intercepts, well, there is no x-intercept because it never crosses the x-axis, so there can be no x-intercept. And with the simple exponential function, b to the power of x, to find the y-intercept, all we have to do is plug x equal to 0 into there. But that's always equal to 1, which you can see here. So for very simple exponential functions, the y-intercept is at 1. And the end behavior, of course, as x goes to negative infinity, as it goes to the left, the function, I'll write like this, exp for the exponential function, this goes to 0 because it gets closer and closer but never hits it, so that's where it goes. As it goes to positive infinity, you can see that it just shoots up to positive infinity. So the exponential function goes to infinity. That's kind of the baseline measure or baseline analysis of this function. Each choice of base changes how the function looks. But there's lots of similarities between them. So we're going to be looking at these four different bases: 2 to the power of x, 1/2 to the power of x, 10 to the power of x, and then 1/10. So 2 to the power of x, this we've already seen. It's the basic exponential function like that. Now the next one I want to show is 10 to the power of x. You can see that it goes down to, as we go right to left, it goes down to 0 faster, right? It's much faster to get to 0, whereas 2 to the x takes a little bit more time. And then on the right-hand side, as we go left to right, 2 to the power of x goes slower up to infinity, whereas 10 shoots up faster. So the higher the base is, the faster it goes to 0 on the left-hand side, and the faster it goes to infinity on the right-hand side. Of course, all of these numbers are evaluated in the domain for both of these functions. It's just you have to go up extremely high before you see them. Like for 10 itself, I have to go up to, well, 10 to the power of 10. that's 10 zeros on the end of it. So you have to have an extremely high. I guess I can show you. For y, we have to have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 zeros after the 10 value. You can see we're just now reaching 10 to the 10. So it does go there. It just takes an incredibly long time. Okay, now I'm going to turn off this and show 1/2 x. You can see here that 2 to the power of x goes this way, and 1/2 to the power of x goes the opposite way. And that's the big thing between b greater than 1. b greater than 1, it has this red function, is what you expect. And when b is between 0 and 1, that's where this blue function shows up. It's this opposite behavior. It's actually flipped across the y-axis, this one specifically because we have 2 to the power of x and 1/2 to the power of x. And I'll show you why that is in just a second. But it's the opposite way. However, it has the same kind of behavior. To the left, it goes up to positive infinity very quickly, and to the right, it goes to 0 very fast. Of course, not as fast as something like 1/10 to the power of x. Just like how 10 to the power of x went to infinity faster than 2 to the power of x, and went to 0 faster, 1/10 to the power of x, which is this orange line here, this goes up to infinity on the left-hand side fast. On the right-hand side, it goes to 0 faster. So it's faster than the blue line. That's what you kind of expect. So for all of these functions, I should say, let me graph them all real quick. For all of these functions here, you can see that there is a horizontal asymptote at 0. They never cross that. And this is, of course, for these baseline functions here, these 4 basic functions. There's always going to be that horizontal asymptote. If it's transformed, shifted up or down, then that would not be the case. But we have a horizontal asymptote at y equal to 0. Now, for f of x equal to b to the x, then f negative x, it's going to be b to the power of negative x. But that's just 1 over b to the power of x. And so you can see that when we plug in negative x, according to function transformation, if you plug in, this is b to, I suppose it's going to be a little confusing because we have this b and then that b. But think of function transformation. So a, b, c, and d. Don't confuse this b with this b. They're actually different b's. This is function transformations, bt. AT, B, CT, and DT for transformation. So if BT is equal to -1, that means we have a horizontal flip. It's flipped across the y-axis. And we get 1 over b when we simplify that statement down. So this is 2 to the power of x, And 1/2 to the power of x is a horizontal flip across the y-axis from the original function. And that's all it is. That's the reason why it looks this way. Because negative x, just actually using rules of exponents, changes it to 1/2 x. That's the key thing to keep in mind there. Now, if b is greater than 1, that was like 2 to the power of x goes like this. If b is greater than 1, then f of x is increasing. If f negative x, if we have that instead, then we had a function like this. This is decreasing. Now, if it's between 0 and 1, that's of course just this function here. Think of 1/2 x to the power of x. This was 2 to the power of x. Then f of x is decreasing. And of course, the inverse, or if you plug in negative x, you're going to get the flipped version again. That's increasing. Okay, so function transformations works the exact same way as we've been looking at. So this base function is 5 to the power of x. And we're looking for the domain range, the transformations, intercepts, intervals of increasing, decreasing, and constant behavior. So this is the basic function, right? We expect this thing to look like this, just 5 to the power of x. And we have all these transformations on. So here we have a equal to -4. B is just 1 here, right? It's just 1 on that one. C equals +3. And D equals 2. So since C over B is just 3 over 1, so 3, we know it's going to be shifted. And we also know it's going to be shifted up. So shifted right 3 units, shifted up 3 units. But not before we do a vertical flip. And then a stretch by a factor of 4. Then we're going to shift right 3 units, up 2 units. So this is going to be vertically flipped. So it's going to look like this instead. And it's going to get shifted, it's going to get stretched downward and then shifted right and up. So it's going to be just a little bit different from that one. Now, the domain, range, and intercepts, well, the domain is always the same. Domain, we have -infinity to infinity. The range, however, you remember, is from 0 to infinity for this one. But now it's been flipped. So it's going to be from -infinity to 0. Then the stretch doesn't change the range. The shift right doesn't change the range. However, the shift up changes the range. So from -infinity to 0, now it's getting shifted up 2 units. The range is going to be -infinity to 2. So the horizontal asymptote is no longer at y equal to 0, but it's been shifted up 2 units. So it's at y equal to 2. Okay, the intercepts. Now that we do have an intercept, because it's been shifted up 2 units, we do have an x-intercept. For that, we're going to have to actually solve this equation. We can look at a graph and find it using Desmos, but we can just solve it here. -4 times 5x minus 3 equals, I'm just going to divide by 4 as well. So -2 over -4. This is going to be 1/2. Take the inverse of this. That's going to be log base 5 of both sides. And then add 3. So our x-intercept is at log base 5 of 1/2 plus 3. Our y-intercept is a bit easier to calculate. All we have to do is plug x equal to 0 into there. So we get 0 minus 3 is negative 3. 5 to the power of negative 3 is going to be 1 over 5 cubed. So that's 1 over 125. So we're going to get, calculating that out, let's just go ahead and get a decimal number for that. The y-intercept is at 1.968. Okay, so there's our intercepts, x-intercept and y-intercept. And the last question was intervals of increasing, decreasing, and constant behavior. Well, it looks like this, right? It's been shifted over and up, but that doesn't change the overall behavior. So the function is decreasing on its domain, which is the entire domain. All right, next function. We have the basic function is 1/3 the power of x. We know that this looks like this. The same thing as 1/2 or 1/10 the power of x. And we know that c equals 2, negative 2, and d equals negative 3. Since b is also 1 here, right? A and b are 1. That means it's been shifted left 2 units and down 3 units. So the domain and range, the domain is always going to be everything. There's no issues with that. The range, well, it has an asymptote at y equal to 0. And it's been shifted down 3 units. So now this asymptote is at y equal to negative 3. So it goes up to positive infinity and all the way down almost to negative 3, but doesn't hit negative 3. So that's the new range. Okay, the intercepts. So we have to solve for when it equals 0. I'm going to add 3, then take, let's do it like this. We're going to add 3. I'm going to change this base to be 3 to the power of negative 1. And then I'm going to multiply these bases together, or these powers together, by the rule of the exponents. This is the same thing as 3 to the 1 power. And now you can see I have the same base on both sides. That means the powers must be equal. Add 2 and then divide by negative 1. That's going to give us x equals negative 3. So the x-intercept is at negative 3. The y-intercept, plug in x equals to 0 in here. We get 0 plus 2 is 2. 1/3 squared is 1/9 minus 3. So we have 1/9 minus 3 over 1. That's going to be 27 over 9. Subtract those, we're going to get negative 26. Negative 26 over 9. So there's our intercepts. And this behavior, well, it looks like this. It hasn't been flipped at all from this. It's been shifted down 2 units, but that doesn't change the interval of increasing, decreasing, constant behavior. It's always decreasing. So this is decreasing on its entire domain. Okay, let's actually graph these things and see what they look like. This first one, I have 5 to the power of x and this graph itself. So 5 to the power of x is this red line here. So this point here had been flipped downward to this point here. Then it's been stretched by a factor of 4. So it's been stretched, let's see, 1, 2, 3, 4. So, well, I should say it was 1, so it's going to multiply by 4. So it gets to here. Then this point has been shifted over 3 units. 1, 2, 3, and then up 2, 1, 2. And it puts us right at this spot here. So this point got transformed to this point here. And the rest of it, is transformed as well, according to the function. These functions are a little bit harder to see because the powers on there makes them look weird. There's not really nice. This one's pretty nice, so is this one, but the rest of them are pretty hard to work with. So I like to always look at this point here, the y-intercept, and see how it transforms to make sure it does what I had said it did. Okay, it goes all the way up to 2, but does not cross it. That's what the range is here. Goes up to 2. The y-intercept was at 1.968. Same thing I found there. And the x-intercept, let me calculate this on Desmos here. That's what I calculated for the x-intercept, and the x-intercept here is 2.569. So I got the same number as they have here. And of course, it's decreasing on its entire domain, as I said right there. Okay, the next functions is 1/3 and the transformed version of that. You can see this is 1/3. And then it's been shifted. This point here has been shifted. Let's see, it was, left 2 units and down 1, 2, 3 to this point here, it looks like. Yep. The domain and the range is now -3. You can see there's an asymptote here at y equal to -3. X-intercept is -3, y is -26/9, x-intercept is -3, y is -26/9. That's going to be -2.8888, which is what I have there. And it is decreasing on the entirety of its domain, which is what I found there. All right, give it a try in number 1. Now, here is a sample problem using these things in some kind of scenario. For each year t, the population of a forest of trees represented by this function. And in a neighboring forest, the population of the same type of tree is represented by this function here. So which forest population is growing faster? And then which has the greatest number of trees initially, and then by how many? So which population is growing faster? Well, we know that the faster growth happens with a larger base. And we can see here that B has a larger base of 1.029. So B grows faster. Since it has that, it's got 0.004 larger base. So B grows faster. Which had a greater number of trees initially? Well, that's the same thing as asking at t equal to 0. At t equal to 0, what do we get? So a of 0, that's going to be 0 here. So 1.025 to the 0 power, that's just going to be 1, and we get 115. For B0, 1.029 to the power of 0, that's going to be 1. We get 82 times 1, 82. So A has greater number initially. There's a larger starting value. And by how many? Well, that's easy to do. You're just going to take A of 0 minus B of 0. So 115 minus 82. $33. That's how many more it had starting off. Okay, assuming the population growth model continues, so because these models are only ever effective for the period that they're defined in, for some historical period, there's no way to know if they're going to model it for the next, 1,000 years. There's lots of things that can happen to change that. But assuming it does, which forest will have the greater number of trees after 20 years? So we're going to do A of 20 going to be 115, 1.025 to the power of 20. 115 times, let's do that in the calculator, 1.025 to the power of 20. 1.6386 approximately. So I'm getting about 188 trees. Now B of 20. Note that we said that B grows faster, right? So we're curious, is it growing fast enough in 20 years time that it overtakes A? Because it will at some time overtake A. It's 82 times that, so 82 times 1.7714. So of course this number is larger than this number, so we know it's growing faster. But if we multiply it by 82, we still only have 145 trees in B. These are of course approximate, but so B hasn't overtaken A yet after 20 years. It's still, let's see, 43 trees off. So A has 43 more trees. Okay. Well, the next question is, well, let's extend this out a little bit and ask, after 100 years, does it have more trees? Well, A of 100. 115 times 1.025 to the 100 power. Multiplying that all out. I'm getting 1,350, about 1,359 trees. B of 100 is going to be 82, 1.029 to the 100. I get 1430 approximately. So but by the time 100 years have passed, that's when B has outgrown A. Even though A started with a lot more trees, what matters is the growth rate in the long run.